Hi everybody. Our new subject today is determining molecular shape. It is clear from this figure. If you look to this figure, we have three atoms here, and the important thing in this figure is the bond length here and the angle between two bonds. Okay, we can start it. We can now use Lewis structure to determine the shape around a particular atom in molecule. Consider the H2O molecule. The Lewis structure tells us only which atoms are connected to each other. That meaning, if we say H2O, that meaning H bonded to the oxygen atom and the oxygen atom bonded to the other hydrogen atom. Okay, but it implies nothing about the geometry. That meaning the real geometry for this molecule, it is linear, it is bent, something else. Lewis structure actually don't tell us something about the geometry. What does the overall molecule look like? Is H2O a bent linear molecule? 2. Variable defined a molecular structure. That meaning we have two important factors for determining of the molecular shape: bond length and the bond angle. The first factor is the bond length. Okay, bond length is average distance between the centers of two bonded nuclears. Look, we have this atom, for example, two atoms, and the center of this atom, the nucleus, and also the center of this atom, the nucleus. The distance between of them from here to here is we call bond length. Okay, bond length are typically reported in picometers. Okay, whereas 1 picometers is equal to 10 minus 12 meter. Okay, this is very small. And he said here, for example, the oxygen hydrogen bond length in H2O is 95.8 picometers. Average bond length for the common bonds are listed in the table. This is the table. Here, the hydrogen 74, the carbon hydrogen. Look, the carbon hydrogen is longer than the hydrogen. Okay. Is dependent on the size of the two atom bonds, and the other, look to the halogen here. The halogen atom is big atoms. For this reason, the distance between the halogen and the hydrogen, it will be bigger than the hydrogen and the hydrogen, or the carbon and the hydrogen, and the other like that. And bond length decrease across a row of the periodic table, okay, as the size of the atom decrease. Look, when the size of the atom decrease, that meaning the length of the bond, it will be also decrease. Okay, now the bond length, it will be increase from the right to the left of the periodic table. Okay, from the right to the left. Bond length increase down a column of the periodic table as the size of an atom increase. Okay, decrease the number of electrons around the atom, it will be increased. That meaning the size, or the cloud negatively charged, like the cloud of electrons around the nucleus, it will be an increase. Okay, it will be an increase. That meaning the size of this atom, of that atom, it will be an increase. That meaning the bond length, it will be an increase. And the second factor is the bond angle. Bond angle determines the shape around any atom bonded to two other atoms. Okay, that meaning at least we must have 3 atoms bonded together, and we can determine the bond angle between the 2 bonds. That meaning you have at least 2 bonds. Okay, 2 bonds to determine the bond angle. Okay, that meaning if you have 3 atoms like this, 1, 2, 3 atoms, and there is bond between this and this. That meaning this molecule, for example, this molecule have 2 bonds. This bond number 1 and this bond number 2. And the angle here, you can see the angle between this and this, it will be how much? It will be 180. Okay. And if you have another atom bonded to this atom, okay, now this angle here between this and this, it will be 90. Okay, it will be 90 because this bond is actually vertically on this bond. For this reason, it will be 90. Okay, that meaning to determine the bond, we have at least 2 bonds on the molecule, and you can determine the bond angle between the 2 bonds. Here, say to determine the bond angle and the shape around a given atom, we must first determine how many groups around the atoms. How many groups around the atoms? Okay. Then, what type of the groups? We don't say how many atoms around the atom. Okay, we said here how many groups around the atom, because the groups here maybe it will be atoms or lone pair of electron. Okay, that meaning if I say to you here this atom surrounded by 3 groups. Now the 3 groups here, this and this and this, are atoms now. Okay, but for example, if I say to you for the H2O molecule, hydrogen, oxygen, hydrogen, and we have here 2 unshaped of electron. That meaning the oxygen now surrounded by 4 groups. 2 of them are the hydrogen atoms, and the others are unshaped of electron. Okay, now that meaning the oxygen surrounded by 4 groups. Okay, not 2, 4 groups. Okay. Then we use the valence shell electron pair repulsion, VSEPR theory, to determine the shape. Okay, repulsion يعني تنافر. Okay. This theory based on the fact of electron pairs repel each other. Okay, that meaning if you have two group, it will be repel each other for the very far distance between of them. تنافر بين المجاميع. The most stable arrangement keeps these groups as far away from each other as possible. Okay, now I will give you here example. Okay, okay, if you have a molecule from the 3 atoms, that meaning 1, 3, 1, 3, 4. Okay, this 3 atom bonded to each other. Now if I say to you anyone is more stable, figure this or this. 1, 2, 3. Okay, of course this it will be more stable from this. This not stable. Why? Because the repulsion between this group, look, between this group and this group, it will be here 180. That meaning the distance between this and this, it will be so far, but the distance from here to here is a small distance. That meaning the repulsion it will be bigger than this figure. Okay, for this reason it will be this shape or this geometry for this molecules, it will be more stable than this. Okay, here we say the repulsion between the groups. Okay, the second row elements has only 3 possible arrangement defined by the number of groups surrounding it. Okay, that meaning all the elements in the second row in the periodic table has 3 possibility for the arrangements, okay, or 3 possibility of the geometry. Okay, atoms surrounded by 2 groups, that meaning this molecule will be linear. Atoms surrounded by 3 groups, that meaning this molecule will be triangle planar. Atom surrounded by 4 groups, that meaning this molecule it will be tetrahedral geometry. Okay, and for the 2 groups, the best geometry, if the angle between the 2 bonds it will be 180, and for the triangle planar, the best geometry if the angle between 2 bonds it will be 120, sorry, and for the through groups the best geometry if the angle between 2 bonds it will be 109.5 angstrom. Okay, the bond it will be determined by angstrom. Okay, now 2 groups around an atom. Any atom surrounded by only 2 groups is linear and has the bond angle 180. Now he said here to examine the illustrating has this geometry are BeH2 beryllium hydride, and for the acetylene hydrogen carbon triple bond carbon hydrogen CH triple bond CH. We consider each carbon atom in acetylene here in acetylene. Okay, and because each carbon is surrounded by 2 atoms, for each carbon surrounded by 2 atoms, that meaning this bond it will be 180 linear and this bond it will be 180, and for this reason the acetylene it will be linear. Okay, the acetylene it will be linear. Also the beryllium hydride it will be linear molecular because the beryllium atom surrounded by 2 hydrogen, that means 2 groups, and for this reason it will be the best arrangement or the best repulsion between the 2 hydrogen atom. It will be 180 for the angle between the 2 bonds. Then he said here, acetylene illustrated another important feature: ignoring multiple bonds and predicting geometry, can't count only atoms and lone pair. Then don't worry about the triple bond or the double bond. You have just to determine for how many groups surrounded by the atoms. Okay. Now for this carbon, we have 2 groups surrounded. Okay. That means carbon and hydrogen. For this carbon also just surrounded by 2 groups, hydrogen and carbon atom. That meaning we said 2 groups it will be linear. Okay, just draw like linear. Why linear is the best? Because this group it will be so far, the distance between this and this it will be so far, that meaning it will be less repulsion. Okay, less repulsion between the 2 groups. Also between this and this it will be less repulsion, and the distance between this and this it will be so far if the angle between this bond and this bond it will be 180. 3 groups around an atom. Any atom surrounded by 3 groups is trigonal planar and has bond angle 120. And the example states this geometry are BF3. Look to the BF3, boron trifluoride. Look the boron surrounded by 3 groups. That meaning the best geometry it will be trigonal, مثلث, trigonal planar, and it will be planar. It give the best far distance between the 3 group. Okay, less repulsion. Okay, And for the adenine, also look to this carbon surrounded by 3 groups. 1, 2, 3. That means it will be triangle. Okay, 1, 2, 3. Don't look to the double bond. Okay, no difference between double bond, triple bond, single bond. Okay, and the distance between this bond and this and this, all the distance, it will be 120. Now for groups around an atom. If we have an atom like this carbon surrounded by 4 groups, 4 atoms or maybe atoms with n shape of electron. That meaning the figure or the geometry, it will be tetrahedral. Okay, tetrahedral. Tetrahedral, that meaning three trigonal surface. Look, this it will be trigonal, and this it will be trigonal, 2 and 3 and 1 on the down. This arrangement keep 4 groups further apart than the square planar arrangement, in which all bonds angle will be 90 degrees. That meaning the best if we put the carbon in this figure, okay, like square planar. That meaning this the angle it will be here 90, and the distance between 2 hydrogen it will be small. But here in tetrahedral, look, the angle it will be 190. That meaning the distance between the hydrogen atom it will be longer. That meaning the preferred geometry it will be tetrahedral, and square planar it will be not good. Okay, and here how can we represent the 3-dimensional geometry of tetrahedron on the 2-dimensional piece of paper? That meaning how we can understand the tetrahedral geometry on the paper, how we can draw this geometry in the paper. Okay, now we have a solid line. A solid line is used for a bond in the plan. Okay, on the plan, that meaning the bond on the paper, which use for the bond in front of the plant, front of you. Okay, front of you, near from you. Okay, a dashed line is used for a bond behind the plant. Okay, in the back side, far from you. Okay, behind the plant. And look to this figure. This is the solid bond. That meaning this is the bond on the plane of the paper. But here the wedge bond, this in the black color, that meaning this hydrogen near from you. Okay, in the front side. And this is the dashed bond in the back side, the behind of you. Okay, the behind in the far way. Okay, in the other side. And you have to use your imagination to understand the geometry for the molecular. Okay, use your imagination, please. This is just one way to draw the tetrahedron for the CH4. We can turn the molecule of many different ways, generating many equivalent representation. Okay, like this ball and stick. And we have different here representation for the CH4. All of them is right. Okay, but I want from you to understand what meaning the dashed and the wedge bonds. And this homework for you: draw 2 different 3-dimensional representation for the CH2Cl2. Okay, draw 2 different 2-dimensional representation using wedge and dashed bonds. Ammonia, NH3, and water, H2O, both has atoms surrounded by 4 groups. Okay, in ammonia, 3 atoms. The nitrogen surrounded by 3 atoms and 1 n-shape of electron, but in the H2O, the oxygen atom surrounded by 2 hydrogen atom and 2 n-shape of electron. This is the difference. And because we have one shape of electron, that meaning the molecular shape referred to the trigonal pyramid. Because one of the groups are nitrogen is non-bonded electron pair, because there is just one bond, non-bond of electron, and the angle it will be between the atoms, it will be 107. Okay, not 109 and half. If you have 4 atoms, okay, less than 109, it will be 107. And the same thing in the H2O molecule. The angle between the bonds, it will be 105, and give you if you focus on the hydrogen and carbon and the hydrogen, the shape it will be not linear for this 3 atoms. It will be bent, okay, but overall the geometry of the H2O molecule, it will be tetrahedral. Here said example, determine the geometry around the indicate atom in each species. Okay, now he said here the geometry for this atom. Okay, this atom surrounded by just 2 groups, one from here, one from here, that meaning it will be linear. And this atom, the nitrogen, surrounded by 4 groups, it will be tetrahedral. And it's so easy. Remember this table again. Okay, memorize this. It is so beautiful and so useful to resolve the question. Drawing organic structure. Drawing organic molecule presents a special challenges. Because they often contain many atoms, we needed a shorthand method to simplify their structure. And that meaning we have a useful method to draw the structure of the compounds. Okay, the 2 main types of the shorthand representation used for the organic compound are condensed structure, يعني التركيب المكثف condensed structure, and the skeletal structure. Okay, التركيب الهيكلي. Now for the condensed structure are most often used for the compounds having the chain of atoms bonded together, okay, rather than the ring. The following convention are used. All the atoms are drawn in, but the 2 electrons bond linear are generally omitted. Okay, now you have to draw all the atoms, okay, but with no 2 electrons bond. That meaning, again, draw all the atoms that bond to each other without bonds, like that. Look, just CH3, CH2, CH2, CH2. There is no bond here. Now, atoms are usually drawn next to the atom in which they are bonded. Okay, CH3, 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 like the atom. It will be draw to the next atom. They are actually bonded together. Parentheses are used around similar groups bonded to the same atom. Okay, I will explain this. Maybe here we have it. Okay, like this. CH3, look, CH2, CH2, that means this CH2 is like CH2, okay? We can write it like that, CH3, CH2 by 2 CH3, okay? To be shorter, okay? To be shorter, because this is condensed structure. Lone pairs are omitted, okay? There is no necessary to draw the lone pair on the atoms, okay? To interpret the condensed formula, it is usually best to start the left side of the molecule and remember that the carbon atoms must be tetravalent. A carbon bonded to 3 atoms become CH3, and the carbon bond to two hydrogen atom becomes CH2 and so forth. And we have here example. Look, this CH3, CH2, CH2, CH3. It will be condensed structure CH3, CH2, CH2, CH3. Okay, this condensed structure. Or you can use the parentheses. Okay, the parentheses. Okay, look, this CH2, it is like this CH2. That meaning it will be CH2 by 2. Okay, because the similar group. Okay, now look this. CH3, CH, CH3, CH3. That meaning we have carbon CH surrounded by three groups CH3. I think CH3 by 3 CH condensed structure. تركيب مكثف. Okay, now look to this. Look to this CH3, CH2, CH, CH2, CH3, and CH3. Huh? Okay, and the same thing is CH3, CH double bond, CH, CH3. And the same thing here, CH3, CH, CH2, and from here CH3, this CH3 like this, it will be CH3 by 2. CH, CH2, OH. Don't draw or don't put the lone unshape of electron. Okay, the unshape of electron, it will be omit from the structure. Okay, now convert each condensed formula to Lewis structure. That means if you have condensed formula, convert to the Lewis structure. Okay. This CH3 by 2, that meaning you have CH3 bonded to the CH and oxygen. Of course, there is two unshape of electron on the oxygen, and CH2, CH2, CH2. That meaning this Lewis structure. Okay, start at the left and proceed to the right. Okay, from the left to the right. Start from the left here to the right. Making sure that each carbon has 4 bonds. Give any heteroatoms enough lone pair of lone pair to be as octet rule. Okay, for the halogens or for the atom. For this example, the oxygen here has 2 bonds. That meaning to be in octet rule, we have to put 2 unshape of electron on the oxygen. Look here, this Lewis structure, CH3, carbon double bond, oxygen, hydrogen, CH3, CHO. Okay, that meaning the carbon here bonded to the hydrogen and oxygen. And here CH3, CO, CH3. This on the upper side, Lewis structure, on the down, the condensed structure. And the same thing for the other. The skeletal structure. Skeletal structure are used for organic compounds containing both ring and chain of the atoms. The 3 important rules are used to draw the skeletal structure. Rule number 1: assume there is a carbon atom at the junction of any 2 lines or at the end of any lines. That meaning, look to this line and this line meeting here. That meaning we have carbon here, or we have carbon at the end of the line. Okay, assume there are enough hydrogen around each carbon to make it tetravalent. That meaning this carbon to be tetravalent, that meaning must has 3 hydrogen atom, and here must has 2 hydrogen atom, and here 2 hydrogen atom, 2 hydrogen, and here 3 hydrogen atom. Okay, and I will give you example here. Don't say. For example, I write it this. What meaning this? This for the end of line, that meaning we have carbon, and here also we have carbon, and this carbon to be tetravalent must has 3 hydrogen atom, 1, 2, and 3, and this also 1, 2, 3. That meaning this compound is ethane, Okay, CH3, CH3, the ethane gas. Okay, and this will be propane, and this propane, butane, pentane, hexane, like that. Look here, CH3, CH2, it will be like this. 1 carbon, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It is like it is easy to draw the structure by using skeletal structure for the organic compounds. Okay, and the condensed structure, it will be CH3, CH2, 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 CH3. Also the cycle here, the cycle. For every carbon here we have 2 hydrogen. Look, 2 hydrogen, 2 hydrogen, 2 hydrogen. This the cyclohexane. Also look to this example here. Here we have for every, we said carbon, carbon. Okay. 2 bonds meet together, that meaning we have carbon here, we have carbon, carbon, and this halogen, chlor, and here we have carbon, carbon. Okay, this carbon to be tetravalent, that meaning it will be CH3, and here's CH3, and this carbon must has 1 hydrogen to be tetravalent, okay? And it will be CH3, this is the Lewis structure. And the same thing here. Look to this carbon here. We have 1, 2, 3 group, that meaning we remaining just 1 hydrogen, and this is the 1 hydrogen here, and the same thing is CH3, carbon, carbon, CH3. Look, and this CH3, CH3 here, there is no hydrogen. Why? Because the carbon here is tetravalent. Okay, don't need excess hydrogen. Here trivalent, that meaning the carbon needed 1 hydrogen, okay, to be tetravalent, and here 2 hydrogen OH. This is the Lewis structure with lone pair, and in the skeletal structure we don't write the lone pair, or the lone pair it will be omitted. Here the homework for you: draw complete structure for vanillin, show all the atoms and the lone pair. Vanillin is the principal component of the extract of the vanilla bean. Okay. Try to resolve this homework for you, and see you inshallah in the next lecture. And next lecture it will be the skeletal structure with the charged carbon atom, that meaning if you have one of the carbon with negative or positive charge, how to draw the skeletal structure. And see you. Good luck.